Hi all, this is Alan with Bothell STEM Coach, and today we're looking at the last question in the AP Physics 2 2019 free response questions. And these are my solutions. The solutions aren't out yet. So if I have any corrections, I'll put it in the description below, as well as links to the PDF solutions, which I'll keep up to date with the correct answers or corrected answers. So a student notices many air bubbles rising through the water in a large fish tank at an aquarium. In the figure below, the circle represents one such air bubble, and two incoming rays of light, A and B, are shown. Ray B points towards the center of the circle, and on the diagram draw the paths of ray A and B as they go through the bubble and back into the water. Your diagram should clearly show what happens to the rays at each interface. Okay, B is actually the easy one, because what happens is it's Snell's law. So you always got to look at the perpendicular, and in this case, because the angle with respect to the perpendicular is 0, the ray just passes straight through like this. Now, vector A is a little bit different. I have to first draw the normal vector. That means the vector perpendicular to the surface here. And I have to look at this angle. And basically, when I go for, oh, this is water to air, I missed it backwards. I think when I did the problem, I did air into water when I have the solutions. So if you're looking at the solutions, I mixed up there. So I'll correct those as soon as I can, and I'll make that adjustment. I didn't read this water to air. So basically, the index, basically it should bend further from the normal. So it should bend outward, actually. For some reason, I thought it was a water bubble in air. That doesn't make any sense. So the angle ought to be bigger because the index of refraction is bigger, right? And then when we get to this interface, what should happen is it should go horizontal. Because whatever angle it was here is the same as this angle. I don't know. Will it go horizontal? Let me see. Let me think about it. The angle should bend further from the normal than this one. So let me make that a little bit cleaner. So I draw the normal vector, and this is my angle with respect to the normal vector. I guess it wouldn't be parallel necessarily, as long as the angle increases. So whatever this angle is, it needs to be a bigger angle. So you could make it go down. I don't know if you have to make it horizontal, as long as the angle is bigger over here. I don't think it would necessarily be horizontal. Yeah. So like that, and that would be good enough. Okay. So the bubble has volume V1, the air inside has density rho A, and the water around it has the density rho W. The bubble starts at rest and has a speed Vf and has risen a height h. Assume the change in the bubble's volume is negligible. Derive an expression for the mechanical energy dissipated by drag forces as the bubble rises this distance. And express your answers in terms of the given quantities and fundamental constants as appropriate. Okay, so I have a little bubble here, and it rises up to here, a distance h. Now, let's talk about what's happening. Let's draw a free body diagram down here of what's happening. Well, I have gravity acting on it. I have a buoyant force. Like, why does it even rise? It has a buoyant force. And that's it. Okay. Now, it rises because the buoyant force is greater than the gravitational force. So let's derive some equations for the buoyant force. The buoyant force is equal to... Oh, this is an equation that I don't have memorized. I'm not as good at memorizing the equations for it's rho Vg. Make sure I get that right. Is rho V1g. Now, what's this rho? Rho is the density that I'm displacing, and in this case, the air is displacing water, so it's the density of water. Force of gravity is equal to mgh. So not mgh, it's mg, where mass is rho times volume. But this is the density of air, right? Because this thing is made up of air times g. So it's going to have a net force upward, because we know the bubble rises. So the net force upward is equal to... Oh, actually, there's one more force. They said there's a drag force here. There's also some drag force. I'll call it Fd. So the net force upward is the buoyant force minus gravitational force minus the drag force. Because if it's moving upwards, the drag has got to be down. Okay, and so that equals rho W you know, I could factor out, it's rho W V1G minus rho A V1G minus FD. Okay, so this is the net force. Now, why do we do this? Well, the net force, one of the things that the net force does is as it travels this distance, like this thing gained potential energy, and it also gained kinetic energy, because out here it's traveling at 1/2 VF squared, right? And it also gained some potential energy. So where did that energy come from? It must have come from work done by this net force. So the net work done on the system is the net force done on the system times the distance, right? Work's equal to force times distance. And so we have to do all of this, rho omega. I'm going to factor out V1G over here, by the way, and just make this V1G times rho W minus rho A minus the drag force times D. Okay, that's the work done by the net force on the object. And that has to equal the energy that this object now gained, which is 1/2 mvf squared plus mgh. Now m, you know, when you're doing with fluids, m we use rho times v, right? So this is 1/2 rho v1 vf squared. So this is capital V. I hate the volumes and the velocities that make it kind of like really hard to see. Plus rho v1 gh. And that has to equal this quantity. Now, what are we solving for? We're solving for the work done by drag. So we're solving for FD times D. That's the work done by drag. So FD times D, if I kind of think of it as moving to the other side, move it here. It's this portion, V1G rho W minus rho A times D minus all of this here, 1/2 rho. And what rho is this? This is rho air, right? Because this is this mass referred to the mass of the then V1 VF squared minus rho A V1 GH. And I can factor out a V1G. Oh, this distance is H because it traveled this whole distance. So that's H. V1GH. No, not H. I can't do a V1H. So I have rho omega minus rho A H minus 1/2 rho A. Oh, actually, no, you can't do that. Never mind. I don't know why I'm factoring all that out. What am I going to do? You can leave it like this, technically. I was just trying to, like, I think the best thing to do is maybe just combine these two terms, because you could combine this with this. So this would be V1G rho W minus 2 rho A H, I think. Yeah, minus 1/2 rho A V1 VF squared. You don't actually need to do this simplification. I'm just sort of being picky about it. So, yeah. Okay, good. So that was B. At a particular instant, one bubble is 4.5 meters below the water surface. The surface of the water is at sea level, and the density of the water is 1,000 kilograms per cubic meter. Determine the absolute pressure at this bubble location. So pressure is equal to P naught plus, you guys have an equation for this. Let me pull up the equation. I know you got to flip to the top. Let's see. Rho GH. Right, just due to the weight of the water. That makes sense. P naught is 10 to the 5th. It's atmospheric pressure, because the surface of the water is just the atmosphere. Pascals, those are in pascals. Plus rho of the water, which is 1,000, times 9.8 times 4.5 meters. So I get 144,100 pascals. Okay, that's the pressure there. The bubble has a volume V1 when it is 4.5 meters below the water surface. Assume the temperature of the air remains constant as it rises. In terms of V1, calculate the volume of the bubble is just below the surface of the water. So PV would is a constant, right? Because if it's equal to nRT, and if temperature is constant, then this whole thing is constant. So that means P1, we'll call this P1, V1 is equal to P0, V0. V0 would equal P1 V1 over P0. Pressure at P1 is 144 100 pascals. The pressure at was 10 to the 5th, which is 100,000 pascals, times V1, and so that equals 1.441 V1. If the air in the bubble cooled as it rose, the volume of the bubble would be less than the value calculated in part C. Use physics principle to express. Well, so what happens is, in general, I wrote this in the solutions if you want to see, but basically what's going to happen is as the temperature goes down, so what we assumed before was the temperature was the same. That means the particles inside the bubble are going to like hit the walls and keep the volume, like the temperature is the same. But as the temperature goes down within the bubble, it turns out that then they won't hit the walls with as much force, so ultimately the volume will contract a little bit. Because what's keeping the bubble up is the air particles inside bouncing off the walls. That's keeping it inflated. And so as they slow down, they're hitting the walls with less energy or less frequently, however you want to think of it, and thus the volume will contract. So for 3, the V1 decreases. Okay. So let me know how you did, and yeah, I'll see you in the next video.